Dr. B here, and it's now time for worksheet 7.11, covalent bonding worksheet number 2, bond formulas and isomers. Let's play the isomer game. Try to see how many isomers are possible given a molecular formula. Here's an example. If I said you have a molecular formula of C2H7N, there are two isomers possible. There it is, nitrogen in the middle. There it is, nitrogen on the tip. Notice this obeys the honk rules. Hydrogen has one bond. Yep. Oxygen has two bonds. Well, you don't see it, but I'm sure it's true. Nitrogen 3, bum bum bum. Boom, boom, boom. Looks good. And carbon 4. Yes, and yes. So those are the rules we play by. You really should also add the lone pairs to be complete. Hydrogen has no lone pairs, oxygen 2, nitrogen 1, carbon none. Rewind and write that down if you need to. Also, if the halogens show up, realize that largely these only form single bonds. An isomer means that it has the same molecular formula, but it's arranged differently in space. Clearly, this is a different molecule than this. There's only one way to draw H2O, and I'm sure you know. HOH with two lone pairs on the oxygen, which I did not show. C3H6. I know from organic chemistry to look for that 2n+2 combo, and that means no double bonds. That would be C3H2n+2, so double it and add 2 at 8. I got one double bond equivalent. I'm going to throw in a double bond. You could also learn that, just by playing around. Does it matter where we put the double bond? No, this side's the same as this side, but I forgot. There is another isomer where you draw a ring. Very cute, right? So rings are a very beautiful and creative way to come up with isomers. Every carbon has its 4 bonds, every hydrogen 1 bond, and both are C3H6. Therefore, a ring is sometimes referred to as a double bond equivalent. It removes those two hydrogens at the tips, if you will. Okay, CH4O. Well, that is 2n+2, and I know that O is a spacer, so I think that this is no double bonds or rings, and I know that I should draw a carbon in the center. It forms the largest number of bonds. I'll try it with all single bonds, and it works. There's only one way to do it. This is methanol, CH3OH, an alcohol. N2H4, well, let's assemble it. Nitrogen forms 3, hydrogen 1. I will add those lone pairs, 1 each for nitrogen. And is this enough to satisfy everything? Yeah, look, every nitrogen has 3 bonds. Every hydrogen has 1. This is hydrazine, rocket fuel. Here there are 2 isomers possible. I wonder if one of them is a ring. I don't think so, though, because I notice this is 2n+2. It doesn't need a ring. So perhaps it's just a matter of where you put that oxygen, whether it's in the center, as in dimethyl ether here, or whether it's at the tip, with ethanol there. CF4 should be plain and simple enough. Carbon forms 4 bonds, fluorine 1. That's the only way we're going to do it. I really should have those 3 lone pairs on each fluorine. Chloroethane can only be drawn one way. I can't put chlorine in the middle because it only forms 1 bond typically. Well, and that does have the lone pairs on chlorine. Nitrogen trifluoride. I'll bet that's a nasty beast. That has works out just fine with all single bonds and loaded up with its requisite lone pairs. 1 for each one for the nitrogen, 3 for each fluorine. Fluoropropane, I would say this is, because it's just like C3H8 propane, but with one of the hydrogens replaced with fluorine, so all single bonds should be fine, but there are 2 isomers possible. Can you guess what they are? Fluorine in the center and fluorine on the tip. That's right. If we put it on the other side, it's still 1 fluoropropane. It wouldn't make any difference. And there it is in the middle. And this was a make up your own problem. Okay, that was the covalent bonding worksheet number 2.